Okay, I think it started. Um, so hi. This is a kind of non-scheduled release stream. I was just working on this this afternoon and figured that it was actually quite an interesting part and should at least be recorded. Even if for live streaming it's not an ideal time. Um, I wanted this to be recorded. So what I'm gonna do today is so continue obviously on the iCE40 CPU memory cache design, and more specifically, I want to look at here um, on this diagram that we drew last time. I kind of just put like bubbles for combinatorial logic, and I want to look exactly at what that logic needs to do. Try to write a couple of prototypes in Verilog, just mostly to see what the synthesis tool is doing, draft on paper what I think the logic should look like, and compare the two. See, okay, is the synthesis tool um, doing something that makes sense? I think it's always good to have um, an idea in your mind of kind of the size of the logic that you're expecting, the number of logic layer, that kind of stuff, so that you can just synthesize that part and see if the logic tool understood what you meant, found a solution that's at least close to yours. Ideally it would find a solution that's better than the one you thought of like manually in your mind, in your head. um, Turns out most of the time it's not that way. It actually finds a solution that's worse than what you can do manually, but if it's good enough, yeah, just go with it. So we'll see exactly how that's gonna go for that logic. Um, and then the second thing we're gonna look at is I mentioned that this was just the fast path, right? So that's the data path basically when the CPU access hit the cache. But then of course there's something that's not drawn at all in this diagram is we're gonna at some point need to actually access memories to load cache line from the external memory and save them and stuff like that, which mean at the input of some of these things we're gonna need muxes um, for different value depending in the mode we're operating on. Are we accessing the cache, serving the bus, or are we loading or saving data to from the external memory? So that's the second thing I want to look at is where do we need muxes for all those elements. And actually I think I'm gonna look at that first um, because this might actually be useful to know when we're actually designing the combinatorial logic. We know, okay, do we have to add some additional delay for the muxes and that kind of stuff or not? So let's look at this first. I'm gonna keep the diagram in the corner here and just list what we need to mux for the various elements. Okay, so let's start with the tag memory. So this is the read side of the tag memory, which is reading the tag value, the age, when was the last time that this particular cache line has been accessed, the flags, which are the dirty flags indicating that there is some memory stored in the cache that is not yet in the main memory, and the valid flag, which indicates, okay, is this cache line valid at all, or is it just containing random crap? So, wait, I need to find where I can write here. Wait, where? Okay. tag memory read side. It turns out that for this, I don't think we need a mux at all, because the important information that's in there is, so I'm just gonna, what can I write down somewhere? So I'm just writing, okay, what does the tag memory store? It stores the age, the valid, dirty, age, and the tag, which is the MSB of the address. That's stored currently in the cache for this particular cache line. So on the read side of this information, well, obviously when we're in bus mode, so what I call bus mode is when the CPU bus is accessing the cache and fetching data or writing data to it. What the input to that memory is basically going to be the bus address LSBs. So we just take the LSB of the address and we map that to the cache line index. So that's just selecting some bits. What about when we're in memory mode? So when we're loading or so loading data from the external memory or copying the data, that dirty data that we have in cache and storing it into main memory. Well, I don't think we actually need any information, because the only information that's going to be useful when we're doing that operation is we don't need the valid flag, because it doesn't really, okay. Or what I'm going to say is all the information that we need, the valid flag, the dirty flag, and the tag, when we switch to memory mode, we will already have read them from the tag memory. So that all we're going to switch into memory mode is that we're in bus mode, we do an access that is not a cache hit, it's a cache miss. And from the cache miss, we start a memory operation, either write or read, or both, rather. But when we start that operation, we just fetched all those information from the tag memory, which means it's already available on the output of these buses. And all we have to do is save it in a register, which means in memory mode, we don't actually need to do anything. Which means at the tag memory read side, we don't need a mux at all. It will always be derived from the bus address. So tag memory write side. So what do we need to write in the tag memory when the CPU is doing access? Well, the tag memory stores the valid flag. Well, bus access is not going to change the valid flag. That's just not going to happen. Because valid is, okay, is that cache line loaded with data from main memory or not? CPU access won't change that. Dirty flag. Well, the dirty flag will most certainly change because every time the CPU is going to do a write to memory, we need to set the dirty flag to 1. So in bus mode, we're going to need to write the dirty flag. And something that's going to actually be important later is we will never write 0 to the dirty flag. It's always setting it. So we never clear the dirty flag in bus mode. Because when the CPU writes the data, it kind of makes the cache line dirty, but transition from dirty to clean only happens when accessing the, when we actually flush that dirty cache line back to the main memory. The other thing we need to update for every access is the age. So the age is basically when is the last time that particular cache line was accessed. Because we are implementing a LRU cache, which is least recently used, and to implement a least recently used cache, well, we need to keep track of, well, when was that cache line last used? That's kind of in the name, right? So we need to update the age. So that's the kind of access we're gonna need to do, and the address. The address we're gonna access, which is basically which cache line, which cache line we're operating on, is always gonna be the bus address, basically. Okay. What about where in a memory access mode? When memory address mode, what we're gonna write is, well, it's also the bus address, but it's gonna be a latched version, so it's like a registered saved bus address, so it's not gonna be the same address actually. In the sense that when we have a cache miss, what we need to do is save which address that cache miss was for, and keep that somewhere in the register, so that we know which cache line it was referring to. So we will need a mux at the address input of. So if on our diagram here, we have both data and address line going to the tag memory write blocks, which is this little block here. And we're gonna need a mux at the input of this, definitely, because what we need to feed it is different depending if we're in bus mode or in memory access mode. We will need to be able to write the flags, both valid and dirty. Basically, we write, yeah, when we load a new cache line from memory, well, that cache line is not dirty, it's clean, and it's valid, obviously. So we need to be able to update the flags. We need to be able to update the tag, because well, that's pretty much the reason you load memory well, from the main memory. Is if you have a cache miss, is because you didn't have that cache line loaded. And once you load it, well, you need to keep track of which part of memory you loaded into your cache, and that's the tag. And okay, you might think we need to update the age as well, but turns out we don't, and it's probably going to be easier if we don't update the age in memory mode. Why is that? We don't need to update the age in memory mode, because if we loaded a cache line from main memory, it's because the bus wanted to access it, right? And the bus access that's going to happen after the cache is loaded is going to update the age. So we don't need to update the age. We don't actually need to update the age at that point. I hope that that was clear. But basically, yeah, if we load a cache line because that was a cache miss, the age of the cache line is going to be updated when we're back in bus mode, actually serving the request we were unable to serve in the first place. So that's for the tag mem write side. So something else I will note at this point, because it's not okay. So if we look at the diagram in detail, okay, let me just grab something to drink quickly. So this whole thing is a data pipeline, right? You input the data and it's processed in several stages. And the way it's written here, you can actually input a different address and different requests to the cache at every cycle if you want to. And that's the way, that's definitely the way I want it. Even if when we actually connect it to a pure wishbone bus, that might not happen because the bus won't actually move on to the next until we act the request. We can imagine connecting that to some of the VEX internal buses, which are higher performance and are pipeline memory access bus. So those, you just take a bunch of requests and you queue them. You don't actually have to acknowledge them to get the next request. You just get them one after the other. And if we want to be able to operate in that mode, what can potentially happen is, we fetch a cache line, we have here some data, and then we update it and write it here. So we read the tag memory, we modify it, and we write it. But that write happens later. So what can happen is, let me take a clean sheet. Okay. Let's say that this is the address input. Okay, so let me just draw the clock quickly. Yeah, sorry, I need to. Okay, so that's my clock signal, right? It's a beautiful clock. And here I'm gonna input some data. Let me just draw this. Okay, that's the address input. I'm just gonna copy that a couple of times because that's gonna be the same. So that's the address input here at the input of the cache, basically. The next, I'm gonna draw what the information that we fetched at the output of the tag memory. So what's here? Yes, so I need to change page every time. So the tag memory out. So let's say that we have the address 0, and then address 1, and then address 2, address 2 here. And let's assume that these are, consecutive address, which means they are in the same cache line. Okay. And so the first here, well, this is just invalid. That's whatever came before, whatever. And so here we have the tag memory for the cache line 0, and then here we have the tag memory for the cache line 0 as well, because A0 and A1 are in the same cache line, and same thing here. Whatever, and that just continues. tag memory cache line 0. Okay. Now, the next line is what we put at the tag memory right side. So the first is just invalid, that's whatever was before. Then this port, if you look at the diagram, here, the tag memory right side is in the same pipeline domain, in the same pipeline clock cycle as the tag memory output, because all of this is just combinatorial logic, which means what's here happens at the same time, right? At the same cycle. Obviously, there's a small combinatorial delay, but that doesn't matter. And so here we have the new TM value, okay? But that new TM value is not going to be saved, and let's say that's we output it, but it's only going to be written to memory at the next cycle. It's not only going to be written in the actual tag memory at this cycle, right? So at this cycle is when the tag memory actually takes the data and saves it in the memory array, which means the first time we're gonna see that the output, which is actually, because here at the same cycle we're writing it, we're also reading the one for address 1 here. But what's gonna happen here is the old value. It's still the old value. It's not gonna be the new updated value, because the block RAMs are what's called read first, which means basically if you have a read and a write happening at the same cycle, what you get is the old value at the output, basically. The write happens slightly after the read, which means the value that we have here is actually not the new value, it's still the old one. And the new value will only show up at this cycle. So the new value only happens here, right? But that means that when we use here, when we compute another new value, well, this new value is potentially outdated because we based it on an outdated input value. Do you see the problem here? And so we need to take care of that. So if we go back to this, when we're in bus mode, we do two things. We update the age and we write the dirty flag, right? And what can potentially happen is if we write the dirty flag based on an old value, we could potentially write back a 0, even though we should write a 1 because we kind of missed the value. You see, like here, for instance, we write a 1 because let's assume that this was a write cycle and this is a read. Right, so this cycle is a write to address 0 and this is read at address 1, or even read at address 0, it doesn't matter, it's the same cache line basically. So here we get the dirty flag, which is 0, we update it to 1 here and we write that, but here we get back a dirty flag which is, well, 0, and then when we write it here, we're gonna write it as 0 because it's a read, and so we take the old value, we don't set it to 1. And so we write a 1, then we write the dirty flag back to 0, which, yeah, it's obviously a problem. We need to deal with that. And same thing with the age. You have the same kind of conflict, is that the age might not be entirely correct. So what do we do about that? well, we're gonna just consider both cases independently. The age, I'm just gonna ignore the problem basically, because what's the worst case that can happen? Well, it's supposed to be a least recently used cache, right? But if it turns out that we write an incorrect age, well, the worst case that can happen is that we're not gonna evict the cache line in exactly the right order, which is really not that big a deal. And I'm not actually sure that this can be a problem at all, because yeah, it can be I mean, it's not going to be a problem. We can potentially write the incorrect age, but my point is that it won't matter. We just won't evict the absolute oldest cache line. We might evict them in the slightly wrong order. But if we want it to be like 100% correct and follow the LRU 100%, that would cost logic, right? We would need to add some logic to deal with the potential conflict and that kind of stuff, of consecutive access to the same cache line. And for what benefit? To be entirely correct? Sure. But that's not going to have any impact on real world performance, because like pipelined access like that, which follow each other, are both cache hit in the same cache line, that's not going to happen all that often. And even if it happened, here the consequence is we won't have the 100% correct age, and we might evict a cache line which is not the absolute oldest but the next one over. So really, I'm not spending any logic on keeping that 100% correct, and that's perfectly fine. We identified the problem and we decided that we didn't care about the consequence. That's not going to affect correctness. That's not going to corrupt data in memory or anything. The only thing is that we're not going to be 100% least recently used cache, and I don't care. So that's the first thing. So the other thing is the dirty flag. Well, the dirty flag, yeah, that's kind of important, because if you write back 0 instead of a 1, we potentially mark a cache line as not being dirty, even though it is dirty. And that means that when we're gonna evict that cache line eventually, we're not gonna write it back to memory, and we're just gonna lose whatever write we did, which means we're gonna corrupt memory. So we need to deal with that. That's not something we can just ignore and decide, oh yeah, I'm not spending any logic on that. And the way I'm gonna deal with that is, I noted that the dirty flag, we only ever transition from 0 to 1 in memory bus mode. And if we only transition from 0 to 1, what we can do instead of writing 0 or 1 is use a special feature of the memory block RAM from the iCE40. So if I go to the iCE40 iCE40 Ultra Plus. No, I was on the Ultra Plus page. Wait, let me put that full screen. This. So let's go look at the iCE40 SPRAM. No, I want the memory usage guide for iCE40 device. This. Let me zoom a little bit. Okay. And here, mask. So a very nice feature of the block RAM in the iCE40, which not many FPGA have, as far as I know, is that you can independently mask the write of every bit. And by mask the write, I mean that you can choose if you want to write the bit or not. So instead of writing 0 or 1 for the dirty flag, what we're gonna do is we always write 1, but we decide, okay, do we write it or do we leave it as is? And so this way, the OR functions, where we basically mark, okay, it's the old value or 1 is kind of done internally to the block RAM. And then at that point, we don't have that kind of resolves our pipelining conflict, basically. It's very nice that the iCE40 can do that bit by bit. A lot of, if you look in, I think the Xilinx block RAMs, you can do it like byte per byte, so 8 bit at a time, possibly 4 bit at a time. I think it's 8 bit at a time. So MySkit, it's a byte enabled basically. But here we can do it for just 1 bit, so that's really convenient. And because, as I said, this cache is specifically designed and optimized for the iCE40, I have no problem in using that that feature in this case. So that's how we're gonna deal with the pipelining conflict when writing to the tag memory when in bus mode. I hope that was clear. Okay, let's move on. What do we have? Let me go back to the diagram. So this, right? So we handled the read side of the tag memory. We handled the write side of the tag memory. Pretty much the only, other shared resources is gonna be, well, the actual SP RAM, the single port RAM, which only has 1 port, which is read and write. And so we need to see what kind of access we're gonna have for it. Wait, I'm not in the right window. This is the right window. SP RAM. So I'm actually gonna split it in different, the different bus of the SP RAM. So the address, first thing. So when we're in bus mode and serving the CPU, the address is gonna be composed of the which cacheway has registered a hit, if that was a cache hit. If it wasn't a cache hit, it doesn't matter, so we can just always use cache hit. So that's the first part of the address. The other part is gonna be the index, which is which comes directly from the address. Well, I noted it. So you have the way, the index, and the offset, and both the index and the offset, they come directly from the bus address, just register to bring it in the right pipelining level. And so we have the bus address offset. That's gonna be the address that we need to access when we're in memory mode, and so we're either flushing or filling up a cache line. We need a way number as well, but that's not gonna be the hit way number. It's gonna be which way number we decided to evict and replace. It's gonna be the evict way number. The rest of the address is I'm just thinking. Sorry, give me a second. So my kind of dilemma at the moment, what I'm thinking of is I could actually use the registered address that's here. What I could do is add a clock enable so that when it's a cache miss, that register is no longer updating, which means I don't need a mux because that one is going to be stable and that's going to be the address we're operating on, right? Which would means I can save some register and I can save a mux for the index. The downside of that is that the interface I'm thinking about for interfacing, especially with the PyCore-V and the VEX would no, that would actually work. I think that would actually work. Yeah, I think that works. I think what I can do is here add so let me, if I switch to this, so here that register I can add a clock enable to it and only update it if I'm in bus mode. Because as soon as I have a cache miss, that will not update and this will get stable, which means that mux we discussed before for the tag mem right side, where I said I needed to mux with the saved bus address. Well, I've just saved it in the same register as the one I used for the access when in bus mode, which means I saved a register and a mux. Yeah, that's good. So here it's going to be just the bus address. And I don't need a mux. Great. And here, I don't need a mux either. That's still going to be the bus address index, which is now stable because it was latched when we were still in bus mode. The offset inside of the cache line, however, is going to change because that's going to be some counter because we load the entire cache line at the time, and so we need actually a counter inside the cache line to write all of the address. So that's nice. I just thought of that. It's something I hadn't thought of before. So that's actually very convenient. Okay. So what other port do we have on the SPRAM? We have the write data. So what data we actually input to it, and I'm gonna include the write enable with it because they're kind of linked. So we're in bus mode. Well, the data is, bus write data and the bus write enable and the bus write mask, basically. So just directly the data from the bus, pretty much. Just again, we will need to register here there is a register because you need to it's gonna be the data and the mask. Because on the bus is 32-bit wide, but you need to be able to write byte per byte, right? So there's always a byte mask accompanying the write data. Obviously, the bus write enable here is not just the bus write enable; it's bus write enable and and it's a cache hit, right? We only write data if we actually have a cache line loaded for it. And when in memory mode, the data is that we're gonna write is the data from the memory interface. So whatever we read from the memory controller. The write enable is going to be the read strobe from the memory controller, and the mask is going to be all ones, basically, all zero. So yeah, for the write data port of the SPRAM, we definitely need a MUX, which is 32-bit wide, and you know, basically a full MUX. We just can't avoid it because we need to be able to write data from two completely different places. What other port do we have on the SPRAM we might need to worry about? Yeah, we have the SPRAM read data and the read enable. So the read data, because it's an output of the SPRAM, we don't have a MUX, we just route it both to the bus data output and the memory controller interface write data port. It's just always wired to both, it doesn't matter. But we also have the read enable, and this is an input, and we're in bus mode. We just always read, and we're in mem mode. It's gonna be some control logic to read the data at the right time, basically. We'll get to it when we get to it. So I think that's pretty much all the muxes we need to care about for sharing all those resources. So as we can see, there's not actually that many muxes because we need one for the write data side, which is going to be like 32 bits, 2 port muxes, so that's like 32 LUTs plus the mask, that's another 4, which is like 36 LUTs, which is really not that bad. Here we have a mux for a 1-bit signal, which is really small. For the SPRAM address, we have a mux again, but that's a 2-bit signal, so that's like a really small 2-way mux for 2-bit signal. That's 2 LUTs. And we have the bus address offset, and which is again only a 2-way mux, and that's how many, like 5 bits or something, because that's like 5 LUTs, so that's really small. At the moment we're at like 45 LUTs or something. And here we don't have any mux. Here we actually save the mux for the bus address, we don't have a mux. The age we're not updating. And here the only thing that either we write one or the other. So the tag memory stores the valid, the dirty flag, the age, and the tag, but the age we only write in one mode, and the tag we only write in the other mode. So for those we don't actually need mux, we just need the masking signal, which is control LUTs, a couple of them. And then the only one where we actually have mux, because we write them in both, is the dirty flag, which is really small. So all the muxing for sharing the resources and access between the two different modes is like 50 LUTs or something, like tops. That's what I'd expect just from thinking about this stuff. So the kind of resource usage usage I'm expecting, basically, expecting to see. Okay, so now we can move on to trying to see, okay, how is the tool going to synthesize our logic and or tag memory and stuff like that. So we have three main blocks here. We have the tag memory, we have all the combinatorial logic in between, and we have the SPRAM, right? What I want to dig into a bit is how we can inspect what yosys is doing, or any synthesis tool in general. Here I'm taking yosys because I'm using the open source tool chain, but you can do pretty much the same with any of the tool with varying degree of ease. I would say yosys is definitely the simplest to do that with. So the synthesis, well, let's start with the very easy part. Synthesis of the SPRAM. yosys doesn't support inferring SPRAM, which means you need to instantiate it, which means there is nothing to inspect. Like you literally have to instantiate the SPRAM block as a Verilog, from the Verilog template. If you look at, again, you need to refer to the documentation for this. So we can go to SPRAM usage guide. Yes. Okay. And let me zoom 200%. There you go. That's the primitive you need to instantiate. With there might be some more details somewhere. Yeah, here you have the details of all the ports and how wide they are and stuff like that. But basically, if you want to use it in your code, you basically have to, cut and paste that and use it. So yosys is, well, pretty much not involved in that whatsoever. There's nothing to look at. Okay. Oh, I'm an idiot. I forgot to switch the. I meant to show you that. Sorry. So yeah, on the iCE40, the website from Lattice, you have the SPRAM usage guide here, which you can download. And if you look at it, inside of it, you will find the instantiation template for the Verilog instance. And you have also documentation on all the port and what they do and what kind of width they have. That kind of stuff. Okay, so let's go back now to this. So we're gonna look at the tag memory first because it's on the left and first. So let's look at that. So there are two ways to write it in Verilog. You can instantiate it or infer it. Instantiate it is do it like for the SPRAM. It's just you just look up in the official documentation or the simulation libraries or whatever guide you have, like the template to instantiate exactly one block RAMs and the ports it has. And so that would be, we loaded it here. And so again, you have a description of all the ports and the timings, and more importantly, that's not actually the right template. That's not either. So this one is a little special because you have kind of the raw block, which is the SBRAM 44K, which is like the one that yosys supports, and then you have some other, which are really just wrappers for that one, right? They're really just wrappers to make things a little more easy, but that's the actual hardware physical primitive that you get in the FPGA, and that's the only one supported by yosys anyway. And so here again you have the port, and so you can literally instantiate it and connect the signal like whatever you want. The other option is inference, and inference has pros and cons. The pros is that it's often shorter and can sometimes make it easier to make things configurable, like the width of the memory and stuff like that, and you basically let the tool figure out what the optimal mapping from what you want and what you're asking into physical hardware primitive is. The downside is you let the tool do that, and the tool really isn't always all that smart. And I'm gonna write it using inference here and see exactly how that goes, and see if we need to resort to instantiation or not. So let's do that. I'm just gonna open this. So what I'm gonna write now is a module that represents exactly one of these tag memory block here, and I'm gonna isolate it in a separate module so that changing between inference and instantiation is easier than if everything is mixed up in the design. And it's having it isolated, having the memory isolated in separate blocks can also help inference, not mixing everything up. And I find it generally cleaner than having a memory block inside your main Verilog file and stuff like that. I like to isolate them, basically. Yeah, whatever. So memory cache, tag memory, not V. Default net type none, module MC tag mem. So I want it to be configurable, so I will put some things in parameters and see exactly how the tool reacts to that, and see if it does anything that makes sense. Sorry, I forgot again to switch to this. I'm an idiot. I thought something was wrong. So there, I started writing it. Started writing Verilog. I haven't written much yet. So the first parameter is going to be the width of the index field, which is basically the number of cache line. In my main target is going to be 8, so I'm just going to use 8 here. The width of the tags, 12 bits in my case. And depending on how many ways the cache has, I'm gonna need to store different number of bits for the age of the cache line. Like, how is it ranked? Like, which one is the latest that's been used? Age width, in this case, is gonna be 2. So I'm also gonna generate a couple of helpers. Parameter. So these are not intended to be user set, they're just shortcut and shorter, so I don't have to type index with -1 every time I want to access that particular bit, which is just a notation thing. It's okay. So that module is going to have a read port and it's going to have a write port. Makes sense. Inputs, wire, read. No, it's going to be EL0 read index. And then I'm going to have an output with the age. Wait, I'm gonna age of the tag line, the tag that corresponds to that particular cache line. I need the flags, which is read, okay, is it valid and is it dirty? Then we have a write port. Input, wire, index 0. Okay, then we have basically all these but as inputs. And then I pretty much want independent write enables for every one of these. So I'm gonna put independent write enable for every of these fields because as I said, you know, when I update the I will update the age in bus mode, but I won't update it in memory mode. I will update the tag in memory mode, but not in bus mode. So all of these fields I want to use the mask, and I have independent memory write enabled for every one of these. Right, age, WB. Right, tag, WB. Okay, so that's pretty much the interface I want. Right? Is that correct? Yes, I think it is. So, I'm going to have a local parameter with the total width of the memory plus age width plus tag width, which in our particular example turns out to be 16, which is very convenient. But the goal of inference is that if it wasn't 16, we can hope that the tool would find a combination of block ramps that's somewhat optimal, hopefully. And that's kind of what I want to test here is, you know, is the tool doing something I'm somewhat happy with? We need to actually store that memory word. So memory weight -1, 0, mem, and we need that memory array to be 0 to 1 shifted. This. Now, I'm only using one memory array because I am like 100% sure that if I try to use, you know, independent memory array for valid, dirty, age, and tag, the tool is never going to figure out that it can actually merge all of these into a single memory. It's just going to generate 4 memories independently of one another. So I will make the merge myself, and I'm going to make sure that all the memory accesses are made one word at a time and try to express it as much as possible like a memory, so that the tool recognizes the pattern and actually generates a RAM and not a bunch of flip-flops or 4 different RAMs or that kind of stuff. So I will have a word that is actually the read value. I will myself construct a word that is the write value, and also will construct a word which is the bit by bit write mask. So these are pretty much all the signals that I need, and then I need a process. Always add process. Wait, I need to actually map things to this. So I want to split the read value into read valid, read dirty, read age, read tag, read value. And I want to construct the write value as being write valid, write dirty, write age, write tag. And I want to construct the write mask, as being write valid, write enable, write dirty, write enable. And then I need to repeat the age write enable several times. So it's going to be age width, write age UE. And then I need to repeat the tag write enable a certain number of times. So that's going to be tag width. Wait, that's not what I wanted to do. I want to do this, tag width, write, tag, write enable. There you go. So I constructed my values mapped to the complete memory word, and then I can just describe my memory. Read access, read val is mem read index. And so here I'm going to describe the process of writing to the memory, but bit by bit, basically, which means that's why I need a loop. If write mask e, then mem write index. Okay, I think that's our memory described. So the most likely is a syntax error somewhere, but whatever. So we can try to actually synthesize that in yosys, just that block, just to see exactly, okay, what do we expect? Ideally this, with the parameter that are specified at the top here, that should synthesize to exactly one iCE40 block RAM, because that's what we try to describe. Like every function, every test, everything that I described here, if I was writing it manually, I can do it with one block RAM. So let's see what yosys does. It's gonna be a surprise for me too. So yosys, and I will put an inline script. Let me put that slightly bigger. read verilog mc type mem.d. I want to synthesize for the iCE40. I don't want. I'm gonna use the show. Well, I'm not gonna use the show command at the moment. I'm just gonna do this. Let's see what it does. Yosys not found. Yeah, right. Of course, I need it in my path. Okay. Yeah. So it did synthesize it. As you can see, it came up with exactly 1 block RAM and 5 LUT4. So the 5 LUT4 are kind of unexpected at the first glance. So let's have a look at what exactly it did. And for that, you can use the show command. And what the show command is going to do is show you a graph of the synthesized netlist, basically. Yeah, that's probably a little small. But yeah, that's very small for me as well. So I'm going to try to zoom. So we have our block RAM here, like a giant thing. And we can see the output has been correctly mapped to the various things. So the way you read this is, okay, what square is kind of an instance of a block. So in this case, the block is SBRAM 44K, which is like an iCE40 block RAM. When you have like a small lozenge, is that the name in English? That's the name of a signal. These are as well. So I'm not sure what the difference when they're like you know, with flat side, like octagons or lozenge. I don't know. It might just be the size of the signal, like the size of the text or something. Anyway, and that's like a part selector, like mapping of bits, basically. It's because the interval signal here is actually a 16-bit signal, and what this tells you is that this is taking bits 13 and to 12 of interval and mapping them to bit 1 and 0 of RH signal, basically. So that's just the mapping between bits between different buses. Okay, and so we can look, what did it use? Oh, okay, I see, yeah. So here we can see the LUTs that have been instantiated. And if we look at what they used for, you see all the inputs of that LUT, there's only one input used, there's only one input used, all the other input are forced to 0 here. And that's mostly just because the mask logic, like if you look at the code that I wrote, the bit is being written if the mask is 1, if the value of the mask is 1. In practice, the iCE40 block RAMs, they actually work in reverse, in that the bit is written if the mask is 0. And so that LUT, you have 4 LUTs here, which are just used as inverters, basically. But that doesn't really count, because most likely, if that block was integrated in a larger design, the inverter logic will be packed and merged with the previous or the next LUT. So yeah, those are not an issue. And the 5th LUT that it instantiated is this one. And if we look at all the signal it takes at input, it basically takes all the write-enabled signal, the independent force. This one is connected to I0, this one is connected to I1, this one is connected to I2, this one is connected to I3. And what it generates with it is the global write-enable, basically. So it just takes, because the block RAM has both mask signal that mask individual bits and a write-enable signal that needs to be at 1 if we are trying to write any bits. Yosys is just generating an OR automatically. So technically, we could probably force this one to be 1 all the time and just use the mask. Yosys is using 1 additional LUT to put an OR in there. That's really not a big deal. Now, the advantage of using inference is that if, so I can close this. So here, the results are actually pretty good. That would be totally usable for our use case, and we can use it. We don't have to resort to manually instantiating the SBRAM 40K. The advantage of, as I said, inference is that if we only have two ways and we have a tag width which is 13 bits instead, we can just change the parameter, do the synthesis, and yeah, as you say, like that's the same thing. Or if we have less cache lines, like we only have like 16 cache lines, which is really small or whatever, and we synthesize that, you know, all the ports here, all the port widths, they've adapted automatically, and we didn't have to change our code at all. But it's still using only one, right? Now, ideally, so I go back to 2, 12, and let's say that I want to have 512 cache lines instead of 256 cache lines. So ideally, we should just basically use two SBRAM 4K and probably have the same 5.4. And if we synthesize that, we have so we have two block RAMs, but then we have 27 LUTs and a flip-flop. That is weird. So yeah, like what I would ideally like the tool to do, because the memory width is still 16 bits, right? Which means if we put if we want more depth, you know, if we look at the documentation for those RAM, there are 16. They have different modes. One of them is the 256 entries by 16 bits, but they have another. They have different modes. There's a typo here. What I would like the tool to use is basically use two of these memories and use them in the 512 by 8 mode and put two of them in parallel. Obviously, it didn't do that. What it probably did is still use them in 256 by 16 mode, and then use a mux between the two possible 16 bits output of the two RAM. So let's check if I'm correct. So we're still gonna use the show command and see the results. Look at that. And so here we have the block RAMs, the two of them, and yeah, I mean, if you look at this, you know, I know you can't read, I can't read either, but you can see that these are the block RAMs because they're like the big square blocks. And here it basically, for every output, it generated a signal, one coming from the one RAM and one coming from the other, and then a mix between the two. So yeah, it did exactly what I didn't want it to do. And then it had to generate some logic at the beginning as well to be able to write to one RAM or the other, which costed additional logic levels, and basically it made a mess, right? So it basically didn't do at all what I wanted. And if we look at the synthesis output, so at some points in the log, it executes the memory map pass. Yeah, so that's the one. Let me, oh shit. Let me find it. Okay. So that's the memory BRAM pass here, where it basically evaluates different way of mapping the memory you ask it into a memory that's actually implemented by the FPGA. So it's one read port, one write port, 16-bit wide, 9-bit words, 512 words, and so it has different configuration, right? This one is the one it used, where basically, okay, it selected a 16-bit wide BRAM and 8 address bits, and then use 2 of them with a mux. That's the configuration that I would have loved for it to actually use, but you can see that according to the report, it says BRAM port B1. B1 is the right side of the memory, as incompatible enable structure. So basically, what happens is that this kind of enable trick of where we use the fact that every bit is independently enabled, that you can enable it or not. It couldn't recognize that it can actually do that with the memory, so that I'm not sure why. You can consider that kind of a bug in yosys because you can obviously do it, but on the other hand, it's very hard to be able to support every case optimally and stuff like that, and so the truth is that sometimes you will have to resort to actually instantiate things and do it manually. In this case, I have 2 options. Is I can either try to dig into yosys of why it thinks that, but honestly, like, wow, the code for yosys, like, it's way above my head. Like, I have no idea how yosys works. Or I can basically rewrite that by instantiating the block routes myself. Now, in this particular case, because it does the right thing in my so that it only does the wait, what am I doing here? I'm just trying to get back the 2. Okay, this. It only does the wrong thing when I use, index width 9, which is not my main target case. I would love it to be flexible, but for the time being, I'm just gonna keep it as inference because it does the right thing in my main use case, and I will keep it as a later optimization. I'll just put a note somewhere as when so yeah, it's a note for later. Like, if at some point I want to support like 8 ways or something, or well, not 8 ways, but rather support larger tag memories that require more than 1 block RAMs, I will most likely have to rewrite this particular thing to just instantiate the block myself, rather than rely on inference to do it myself, or hope that yosys has been improved by then. That's kind of wishful thinking. I might open a ticket on yosys actually to see if it's something that's easy to fix for the devs that actually understand how the memory pass works. So let's move on and do the same thing for this piece of combinatorial logic. Just give me a second. Okay. So I had written down kind of the inputs that this combinatorial block has, and the outputs that are expected, and then we can see, or we can generate them. So first, list the input we have, the output we expect. I'm gonna draw some schematic of what I expect the logic to look like. I'm just gonna write, kind of pure vanilla Verilog, and see how close or how far that comes in. And I might write optimized Verilog if that doesn't match exactly what I expect. So let's go ahead and do that. So I'm gonna go to this. Yes, this thing. How am I gonna name this? I think I'm just gonna name it test, because I might end up just cut and pasting that logic in a larger block. Here I just want a separate module so I can feed it to yosys independently to see the results and analyze them separately. But in the end, this whole logic might not be a separate module, or maybe it will be. I don't know. We'll see. Count type, default net type, none, module, how did I name this file? MC test. MC test might have some parameters. So we're just looking at this particular piece of the logic, and so the inputs we have mostly is the address, the input address, and the data directly from the tag memory, right? So, and is that all? Oh yeah, we have also something that will come from the internal state machine or whatever, a signal that tells us if we're in bus mode or if in memory mode. So like we have a mode signal, and we have the address, and we have also if this address is valid, if there is actually a request coming in or not, something that's not shown on this schematic, but the input doesn't have to submit a request at every cycle, so which means we have a valid signal that comes in, and if this is not a valid request, we just don't do anything. Okay, so the inputs are input wire valid, input wire well, yeah, as I said, we do have the address, but do we care? Yeah, that all that logic is not actually. Oh, the only thing that we care about in the address is the tag value. It's the width. Yeah. So I'm just gonna use this, and then. As I said, we also have which mode we're currently operating in. The tag, and that's about it. We also have the result of reading data from the tag memory. Now in Verilog, unfortunately, I can't pass like an array of arrays, which means what I'm gonna do is just gonna pass a very wide signal that represents all the tag memory at the same time, and then like split it into more convenient signals inside the module. But that's really just yeah. Kind of an artifact of Verilog, unfortunately. That's really something that annoys me. Among the things that annoys me in Verilog, the fact that you can't pass arrays of arrays, and the fact that you can't have like empty signals, like signal with zero width, is actually something that annoys me, because if you look at the previous module we had, like if I open the tag memory we just worked on, like the age signal, like imagine that you want a cache that only has one way. Well, the age really is the log2 of the number of ways, but if you only have one way, the log2 is 0, which means you would need a signal, you don't need an age signal at all, which means that signal would need to be 0 width, and that's not something that Verilog supports as far as I know. It's like the handling of the degenerate case of configurability is really not that great in Verilog. That's the other thing that annoys me. Anyway, coming back to this, we have a signal that's gonna be well, okay, I'm gonna need two plus h plus 10 with plus 1. I don't know what I just did. So these are pretty much the inputs we have, right? And I'm gonna write the input mapping first. Wire. Sorry, it takes me a little bit of time to actually write the Verilog. Hopefully, if you're watching the recording, you can watch it at twice the speed. Unfortunately, I can't really type faster. So wire, we need the age. We need the tag. We need the valid flag, and we need the dirty flag. So I need to map basically every field to a flattened array thing, which is fairly common to have to do that, but it's, well, still annoying. Yeah, there's actually ways. Something like this. Light. One page width, tag width is always fascinating. Oh damn it. No. Okay, no, never mind. I know what I'm gonna do. I'm gonna do it like this. In way valid. In way 30. In way age. In way tag. Equal in way man. Then winner. I think that's correct. In way valid, in way dirty, in way age, in way tag, and we take in way man. And I can actually do this. Yes. Let's first just try to see if I have made any. Okay. Oh, I just realized that with my face you can't actually see what I'm typing here. Okay. Let's just see if I made any just stupid mistake in it. Just that city size. Invalid array access, perfect. Line 41. So where did I screw up? Oh yeah, obviously all of these signals, they're arrays, which means I need to actually index them. Because they're arrays and I'm only assigning one of the... That works, no errors, okay, perfect. So these are the inputs that I want. Okay, so no, sorry, the inputs that I have. Now I need to actually list the outputs that I want. So, the first thing I want is if I have a hit, which way, like which way of the cache has actually has the hit, so I know which basically zone of memory I need to access, right? That's the first thing. Actually, the very first thing that I might want is, do I have a hit or not, or is it a miss? That's kind of it's kind of important. I need to know if it's a miss. Now, a miss is not the opposite of a hit, because the input command might have been invalid or nothing. Which, you know, if you don't have an input command, then it's neither a hit or a miss. It's just nothing. That's why I have two independent signals. What else would I have? Wait, I thought about the logic this afternoon. Okay, yeah. Okay, I have an output. So that's not entirely correct. It's ways modified. Okay. So I need to update the age of inside the tag memory. I need to update the age field. So I need the write enable signal for that, and actual age I need to write. And again, I need to use like a flattened array because Verilog. What else do I need? I think that's it. Oh no, sorry. In case there is a miss, I need which way I'm gonna evict. I need the tag. So in case there is a cache miss, I will select one of the ways. So if it's a four-way cache, I have four possible ways. I need to pick one for which the cache line I'm basically gonna evict from the cache and replace it with a freshly loaded cache line from memory. And possibly if the cache line that was previously there that I just decided to evict contained valid data and that data was dirty, I need to first flush that, read it from the cache, write it to memory, and then load the new one. And so that's something I need to know. Yes. Which cache line I decided to evict. Actually, that's multi-bit signal. I need which tag it contained. and I need to know if I need to flush it or not. Is that all? I think that's it. I mean, there is some other signal that I'm gonna need, like the write enable signal for the SPRAM and stuff like that, but that's fairly isolated. That's not part of like the main, you know, cache line selection and validation logic and that kind of stuff. Because the write enable signal for the SPRAM is just going to be a mux between the input write enable signal and the memory mode the memory mode write enable signal. So that's not something I'm concerning myself with at the moment. This is just like the main. Okay, I just realized I'm just okay. This. I'm just concerning myself with all the logic that deal with, you know, reading from the tag memory, validating, and basically taking the main decision, because that's going to be a big part of the combinatorial logic. And so I want it to be small, and I want it to be fast, because the output of that logic is possibly going to need to drive some muxes and some more combinatorial logic. And so I don't want it to be too deep, basically, because if it's too deep, it's going to be too slow. If it's too slow, it's going to make the plus and root harder, and in general, bad thing will happen. Okay, so let's go back to the code. I have my outputs. Well, no, I have my list of outputs. Now I need to see how I can generate them. So I have the input map. I will actually change that to IO map, because I also have the out age signal that I need to map. And so assign out age age width e times by age width just gonna name this outweigh age, this outweigh age fat. Okay, so it's still, yeah, okay. I don't have any syntax error so far. So let's just write some, you know, kind of straightforward Verilog, not trying too hard about what we're writing. I mean, well, no, actually, no. Let's let's try and draft what we think that logic should look like first. Because I mean, I already have in mind sort of what I think the logic should look like. And we actually did think a little bit about it previously when we drew that stuff to kind of estimate the data and stuff like that. But I want something a little more kind of detailed. And so I'm gonna start with that and see how that goes. I'm gonna take a new page for this. Yeah, let's go with this. I'm not sure if that's large enough to be readable. Yeah, I think it's gonna be fine. So let's start with let's start with if it's a hit or not, and which way. Oh wait, give me a second. No, never mind. Yeah, let's start with that. So we have a 12-bit tag. We have 4 of them, and we need to compare them to a reference 12-bit value. Each .4 can test compare 2 signals at a time, obviously. Which mean, as I said, the comparator is gonna be something like wait, actually, and it's one, two, three. We're gonna have 6 slots, and then we're gonna merge that into so each of them is gonna take 2 reference signal and 2 signals. Each of them take 2 reference signal and 2 signals from the tag memory. Now we need to merge that down to one single signal. So one thing we can do is obviously have something like this, and then we have this 4 times for every way of our cache. Now, one thing we can already improve is we also need to test, in addition to the tag itself, we need to test if that cache line is valid. So we have the valid signal of the cache line. So here we input the, wait, what the fuck am I? This part is gonna test the tag, and then we have the input valid of the cache line, and here we actually have a LUT4 that we only use 3 input of. So what we're gonna do is just take the valid input signal and just use that LUT for it as well, right? And then that last LUT here, well, we only use 2 inputs, and really all we need to know is if it's a cache hit or not, which is a single signal. So instead of having, so if we have this 4 times, we would have a final LUT here that merge the 4, the signals coming from all 4 ways, basically, right? And this would tell us if it's a hit or not. I'm just thinking here. But that's not enough. Because for it to be a hit, we need to actually be a hit in the cache memory, we also need to test against mode, and we need to test against was the comment valid in the first place, which means we're gonna need another LUT here testing 2 more signals, right? That would be the logic that we need. But this LUT here, like, we only use 2 input signal, which means we can actually share it between 2 different ways. And so something better is, we just erase all that part. For each way, So we have this repeated for 4 ways. And then we have one LUT shed for 2 ways. So this comes from way 1, and then we have another LUT that's way 2, and that's way 3. Okay, and we have those two outputs. We can combine them in another, that's an horrible LUT for. And so that's better logic. That's our hit signal. And as you can see, we have used 4 layers of logic. We have this, and that's 4 layers of logic. And this, how many LUTs is that going to be? Well, we have 6 here, 7, we have 8 multiplied by 4 ways. That's 32, 33, 34, that's 35 LUTs. And 4 layers of logic. Now, this should actually represent that's most likely the most complicated signal, because we have large comparators, like we have large 12-bit comparators. That's a lot of logic. So I expect this part to actually represent a significant amount of the logic used. If we look at the other signal we need to generate, we need to know which way has actually generated the hit, right? So we can estimate, so if we can keep the same intermediate signals that we have here, and we need to generate which way actually has the hit. Now, we know for sure that only one way can possibly, attack can only be in one cache line, a valid cache line. So this signal is actually already like the MSB of what we're looking for. Because it indicates if we have a hit in way 2 or in way 3. And then we just need to know if we have a hit in way 1 or in way 3. Which means we just basically have another LUT here that takes the signal from way 1 and from way 3, the two of them. So those two signals and those two signals. I'm actually gonna draw it on the bottom. So we have the signals from way 1, and then those from way 3. So to complete the hit way, we just added 2 LUTs, basically. We just added 1 LUT. The other we already had, right? So it's 1 LUT and no additional. It didn't increase the total depth of our logic. So what other signal do we need? So we have the age and which way, okay. So I'm gonna go with the age. How do we compute that? So the age is, I'm taking the example here for 4 ways, so 2 bits of age. And we're just gonna say that 0, 0 is the most recent, and 1, 1 is the oldest. Let me go back to this. So here, that's and then you have obviously all the intermediate values, right? If the cache line is invalid, the age field is meaningless, so we don't care about it or what it is or what it ends up being, whatever. So the next age value, the one we're gonna write, if there is, so let's write the various possibility. If we don't have a hit, well then we don't update the age as well because we didn't actually do any cache access, so no update. That also means that, you know, in the signal that we're generating, that's not what I wanted to do. That's the age value, right? Or rather, that's the next age value. But if we're not writing it, we don't really care what that value is. So we don't need to force it to 0, 0, 0, or whatever. If the write enable is 0, we don't care what the combinatorial logic will output for this. We only care about it if we actually write it, right? That makes sense. So there is another case where we don't write it, is if we have a hit, but that hit is already on the most recent accessed cache line. So if the cache line where the hit happens is already set to 0, 0, then we don't need to update the age. The age is already correct. So yeah, if we have a hit on the most recent accessed cache line, we don't write anything either. And then we have the final case is it on not a recent one. And so in this case, if the cache line is invalid, then we're gonna set the age value to 1, 1, just as kind of a default fallback value so that we don't confuse it with being the most recent cache line. And if it's valid, so if it's a valid cache line, and it's the one that's actually being hit at the moment, we set it to 0, 0. And if it's a valid cache line and it's not the one that's actually being accessed, then we take the old value plus 1. That's essentially what the combinatorial logic for the age needs to achieve, right? So, how is that going to work? Well, as I said, if we don't write, we don't care what the output is, right? Which means when we consider, okay, how do I evaluate the next age value, we only have to concern ourselves with, well, this part. So when we generate the age output, right? And so we have a mux between the old value plus 1, between 0 and 1, 1. So that shouldn't be too hard. So for each of the ways, we can generate an actual signal here that merges those two signals, and that tells us if I'm just if it's a hit, just considering in my head, okay, what's okay, so for every way we're gonna generate two signals. One that says if it's a hit, for that particular way, and we're also gonna generate a signal that says if it's a hit and it's not the latest one, because we can actually take the two input signals, from the pre-match here, and then combine them with the age, and compare that to 0, 0 to see if it's the most recent or not. And so assume that we generate those signals. Then, okay, the right enable is gonna basically be a OR of those 4 signals from the various ways. So we have a alert here that takes the input from that, and that's the age right enable. So we're still at 1, 2, 3, 4 layer of logic, and we have our output signal. And we took 4 and 5 LUTs to generate it. And that generates our right enable. So now we just need the mux here. And so the mux here is gonna be we're generating 2 signals, right? I mean, we're generating a 2-bit signal, so we're gonna need 2 LUTs. Let's assume that we have the old age as the input. And we need what kind of other signal do we need? We need valid. To be able to set it to 1 if it's not valid. Do we actually? I'm thinking, do we actually need that, or do? You know what? We don't actually need that. Yeah. That's I don't actually need that, right? If we'll just consider if the cache line is not valid, the age field is whatever. That age field is gonna get written anyway when we load it, because when we load a cache line from the memory, that will be a cache miss, which will trigger a load from memory, which will result in a cache hit, and during the cache hit, we will write it as 0, 0, which means it will become valid at that point, the age field. Which means I'm just trying to make sure that that's correct. Yeah, I think that is. Could we screw up in... Because, you know, earlier in the stream I said that we didn't care if you wrote an invalid age, not an invalid age, but if we didn't, you know, if we didn't strictly respect the LRU, I want to make sure that things won't conflict here, because what can possibly happen if I rely on the access following the cache load to actually set up the age to 0, 0, is that we just after it we have another access to the same cache line, which will be a hit, and no, I mean if it's a hit on the same cache line, it's gonna get written as 0, 0, which means there's no conflict, which means it's valid. No, it's fine. Okay, yeah, okay. The one thing that concerned me is kind of the interaction with me saying, okay, no, we don't need to write it because it's gonna get written anyway when we load it. But then earlier I said, okay, we don't need to concern ourselves with pipelining conflicts, because if it's valid at some point, the worst case that can happen is that we don't strictly respect the LRU, and I wanted to make sure that we wouldn't read an invalid value and write it again. But the pipelining conflicts only happens if we access consecutively two times the same cache line. But if we access 2 times consecutively the same cache line, it's going to be a valid hit both times, which means we're going to write 0, 0, which means we force the value. And that's the only value that matters where the conflict can possibly happen. The other values are going to be valid. Oh, but no, because the way it holds might not be valid. Wait, what are the cases that can happen here? It's either the signal is going to be 1 or it's going to be 0, right? There's no, it was definitely 1 previously for the first. No, never mind. I mean, either that signal is triggers a write because we're not already 0, 0, or it doesn't because we're already 0, 0, which we end up with 0, 0 in any case. So that's fine. Okay, never mind. It might be something to check in simulation to make sure that I didn't screw up those assumptions, but they sound valid to me. That might have been hard to follow. Sorry about that. That's kind of what's in my head, and that's not always easy to follow even for me. So I can imagine that people watching the stream or watching the recording might not have understood. But the gist of it is, I'm trying to save logic by making assumptions, and I need to keep them in my head to make sure that those assumptions don't actually conflict with each other. Especially when I decide, okay, that pipelining conflict can't happen, or if it happens, that's not something that matters. I need to actually make sure that it doesn't matter. because obviously that's just something, you know, I'm thinking, okay, yeah, I don't see any way it would cause any problem, but sometimes you're just wrong and you don't see something. But if you keep them, I mean, so far we really haven't made that many of them. That's pretty much the pipelining conflict thing is pretty much the only one, and that's something we can check. That will definitely, you know, write a test case for to make sure that it actually behaves the way we expect it to behave and that it actually can't cause any problems. And that will actually bring us to the next output that we. So here we generated those. Sorry, we are generating the age. So we generated the write signal with the way it hits things, and here we need to generate the next age, and the only thing we need is the old value, which is 2 bits, and we need to know if it's a hit or not. And so we don't actually need like this signal, we don't actually need it because we have 2 free input on the lid 4, which means we can just take those 2 inputs directly. So let me just erase that lots. So to generate those 2 inputs, I basically use 2 more LUTs, something like this. So let's go back to the list of signal we need to generate. Here. So we have generated this. All of this we have. We have not generated miss yet, but it's essentially 1 LUT. It's pretty much the same as hit, except not when we're in the right mode under invalid, which means that it's really just another LUT like here. So that's just another LUT. Really simple to generate. What I really want to point out now is that we still have 1, 2, 3, 4 layers of logic, because these depends from those signals which are at level 2, and this is direct input from memory. So we still have a depth of 4 layers of logic. That's the important part here. Next we have all the eviction stuff. So eviction is we need to pick a cache line to evict from the cache. When it's a miss, we need some space in the cache to load some new data. So we need to pick somewhere to put it. Now all that logic is pretty much completely independent of the hit, and all of the logic that we wrote right now is kind of interdependent. You see, there's a lot of signals going to several places because they're kind of interrelated. Picking something to evict is pretty much completely independent. Like we don't care if it's a hit or not. We're gonna pick what to evict if we need to evict, and the selection process for that doesn't matter if we actually need to evict something or not. We'll just not use that signal if we don't need it in the end. So how do we pick who to evict? That's a good question. So, preferably, if a way is invalid, we can select it for replacement, because that means that that data is actually unused, and we should definitely use it. And the other is if it's the oldest, for the LIU algorithm. So the way I see that, what we need is Since the logic is pretty much independent, I'm just going to start a new diagram. For each way, we have the valid signal, and we have the age, which is a 2. And that's a 2. That's not very clear, but that's a 2. So we have one LUT4, and then we basically have another LUT4. Actually, we have 2 of them because we need to generate 2-bit signal. Yeah, so that's pretty easy. Like, for each way, we independently test if it's valid or if it's the oldest. If that's the case, it's a candidate, and then we need 2 LUTs to basically take those 4 signals that tells us if a way is a candidate or not, and just pick one with a priority list, or it doesn't matter. If it's a candidate, we can replace it. Like, I would say ideally we would prefer to replace valid to oldest one, but the truth is, if so we test if the age basically is equal to 1, 1, right? Which is the oldest one. But it shouldn't be possible to have a way that's age 1, 1, which is valid, if not all the other ways are valid. That just shouldn't happen. Yeah, because I mean, it's written, the age is written as 0, 0 during the first access, during when it's loaded, and it's incremented by 1. Wait a minute. Did I screw up the age logic? Because I thought about that age logic some time ago, but I think I might have screwed that up. Because let's imagine that we have a, so we have, okay, let's say we have the way number 0, 1, 2, 3, and then we have the age, and then we have currently age 1, 2, 3. Okay. Let's say that we access this way. Then, well, yeah, completely screwed it up. What did I dream that we needed to set the age plus 1? Because that's, with the current algorithm, what that would yield is basically 1, 0, because that's the one we accessed, and then this one is plus 1, and this one is plus 1, and this one is plus 1 is 0, which is obviously wrong. So, yeah, my algorithm to compute the next age is actually completely wrong. Huh, interesting. Okay, so I'll definitely need to review that, because that's not good. I'm just thinking about, what actual algorithm do we need? Okay, so yeah, this, like this thing, in particular this, that is definitely wrong. I'm not sure yet what the next value needs to be or what algorithm to apply, but it's definitely not that. So if it's a hit, it definitely becomes 0. That's for sure. And this part is correct as well. Like if we hit on the most recent, there is no right. That's for sure as well. And if there is no right. So that part is true. That part is true. That one completely wrong. I honestly have no idea what. I'll need to think about it. I mean, just because here we're just testing the synthesis ability of yosys, I'm just gonna implement that. I know it's wrong and I'll change it later, but I just want to see if yosys does what I expect it to do based on the behavior that I ask him, and not really if the behavior is correct or not really. I mean, ideally it'd be correct, and most of it is correct. At least I think it is. But this I know it's wrong and I need to change it. But for the time being, I'll keep it like that. I just remember that I need to come up with an algorithm that actually works. And so here I'm going to assume that the ages are correct, and that I found an algorithm that works. And so to pick which way to replace, all I need to do is either find a way that's invalid or one which is the oldest, because either there's one that's invalid or one is the oldest. That's like a two possibility, which means for that I need 1, 2, 3, 4, 5, 6 slots. The next value that I need to generate is okay, if I need to, for the way that I picked, if I need to actually flush it and the tag of that. So essentially the tag, the output here, I'm gonna use that to drive a mux, 4-to-1 mux, which is the tag values, which are 12 bits. So a 4-to-1 mux for 12 bits in a LUT4 architecture, that's going to be 24 LUTs. And I need to drive another 4-to-1 mux, which are the dirty bits. I was just thinking, okay, do I need to actually, because it needs to be dirty and valid, right? If it's dirty and invalid, that doesn't matter, but dirty and invalid is in invalid state, which should just not happen, which means I don't need to mask it. I can guarantee that doesn't happen. Because we never write dirty to 1 for cache misses. Yeah, this should never happen. Famous last word. Yeah, definitely. I mean, I know that it's not. It definitely needs to be tested in simulation and check your assumption in a test bench, right? But the truth is, if you try to design your logic assuming that everything is gonna fail, and that and try to recover from every possible failure, your logic is gonna be way too large. And sometimes it would totally make sense to do that, right? Like if I was coding like a life critical system, obviously you want to be error resistant and possibly have concurrent logic and soft error detection and all that kind of stuff. But here I'm aiming for small, and obviously I will need to check that these actually can't happen with actual test cases. But I will try to guarantee those. It's not assumption; it's like invariance, basically, and make sure they don't actually they actually hold true. So another 4-to-1 mux for signal, that's gonna be 2 LUTs. Sorry, I lied. It's not 24 LUTs. It's 36 LUTs, and that's 3 LUTs. So that was a total of 42, that's a total of 45. That's for this part of the logic, and we generated all those signals. And so here, I think, so we have like kind of a diagram of the logic we expect. At least that's the logic that I would be able to write manually. And it goes, so here we have 35, 43. So here I pretty much went into the detail of every signal, right? Usually I won't do that. I will take like shortcuts and try to estimate more grossly so that it takes less time, because I mean, obviously I don't know, and here I spend also the time to try to explain my reasoning and stuff like that. I usually try to do that so that it doesn't take me more than 5 minutes to try to come up with a number of something that I would expect, and I would have probably rounded that to 50 lots, because here I knew that what was most likely gonna cost me most was gonna be the mux for the tag, because I knew I would have to have a 12-bit 4-to-1 mux. I knew that this is going to be 36 slots plus other control logic. I would probably have estimated that to 10 lots, so I would have like rounded to 46 lots or 50 lots. And for this part of the design, I knew that the large part was going to be the comparators and this, which was like a 40 lots as well. So I would have rounded that to 50 lots as well. I would probably have rounded the total logic to like slightly less than 100 lots or something like that. And not necessarily have gone into that level of detail. Okay, so now we actually try to describe that logic in Verilog and synthesize it, right? So let's do that. So the first thing I'm going to do is everything that needs to be repeated for each way. So I just have one generate loop for that. Sorry, let's check something. Wait, so wire. So I need a signal that tells me if I matched on a particular way. And I want also a signal that tells me if it's the most recent age or not. So to be a match, I need in way valid. I need a way to actually contain valid data, and I need I think that's how I named it. And I named that in tag, in address tag. And then I have the same thing, but in addition, I want the in way. Okay. Age to be different from 0, so I can just OR all the bits, and that's Okay, so I can already create out miss and out hit from this. Out miss is gonna be I need the input to be valid and I need the in mode. I mean, I didn't define one. In mode is 0 or 1, but it's gonna be one or the other, doesn't matter. And I need none of the way to match. So I need that or way match. And it's gonna be a hit if it's a valid command in bus mode and there is a match somewhere. I'm gonna use a combinatorial process to select which way matched, basically a priority encoder. So that means this is gonna be a leg. So I need to scan k equal 1. So basically that's just a priority encoder for if there's a match, just take the first match. If there is no match, the hard 8-way value doesn't matter, so it might as well be 0. That's why I'm only testing from 1 to the number of ways, because there's no point in testing for way 0. I also know that there's only going to be one way, because if there are several match in different ways, something is definitely wrong. We need to the cache count function probably in that case, so we need to prevent that anyway. Okay, so we have this. Outway HWE. Okay, assign out HWay. So when do we write? Oh, okay. So I just realized I should probably be in that mode. So when do we write the age? If it basically we have a hit on not the most recent, so that's basically or of this signal. And also we need invalid and in mode. Yeah, actually, I was just checking. if yeah. What else do we have? Outweigh age. So we have the age thing. No, I'm gonna way age, way out age. Is that how I name this thing now? Outweigh age, yeah. And so we said that this value was if it's a hit, 0, 0, else way in age plus 1. And that's incorrect logic. I need to find exactly what it needs to be. I know it's not that, but for the time being, I'm just gonna use that. Okay, what else? We have all the eviction stuff. So these are really just 4 to 1 mux, which I can code them as such. In way, is that how I name it? What did I name it? In way tag, yeah. And then I need sort of priority encoder for this. Out EV way, out EV way. Which means I'm gonna make this register because I assigned it to the process. Out EV way equals 0. So when do we evict if it's the way it's invalid? Or if the way is the oldest, in way age k to be 1. Out EV way equal k. Okay, I think that's actually it. Let's try to run that through yosys and see how that works out. Error. Well, of course. What? Unsized consent must have a weight of 1 bit. 91. So where did I screw up? Yeah. It's implicitly declared and left 68. Wait, what is it name? Oh, it's waste plural. Way out age, okay. And 71. Way out age. Wait, isn't that? Oh, it's out way age. Never mind. Yeah, usually it's in where is. Need to remember how I name my signals. Out age. By the way, that's why I use like default net type none in Verilog, so at least it warns me when I screwed up the name of a signal, because L will just create signal dynamically and then I will just never find that typo and my logic will be optimized that way, and I'll spend an insane amount of time searching why it does that. That's why I prefer to declare all my signal and use default net type none. Where did I use J? It's K. Involuntary access. Okay, that's better. Yeah. Okay. So there you go. That's the synthesis from yosys, which tell me 66 slots. Which honestly I find a little suspicious, because if we go back to that max, I really don't see how it would have implemented that in less than this, and it definitely didn't implement the rest of the logic in 21 LUTs. So 12, I mean a 12-bit 41 max. Yeah, you need 36 LUTs. Like, how did? Okay, well, first thing we can do is let's look at the LTP command. It's longest topological path, which tells you basically the logic depth of the synthesis results. And that tells me 4. Wow. I'm impressed. Actually, I didn't expect that. But okay, nice. I didn't make any errors, right? Let's just, I'm just gonna do, I mean, I probably did an error somewhere because 66 is too little, which means I must have screwed up somewhere. Let's see if I can spot where. Ah, well, that's a problem. Show didn't work. Why? Oh, wait, no, it did. Okay, so that's hard to read. Okay, so that's out EV tag. That's easy to test, and that's a mux. That's a 4-to-1 mux. That's what I expect. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't know why it put that one there, but whatever. And then for each of them, you have another mux. All of that is 36 slots. So that's that part I expect, right? And it's 1 layer, 2 layer. Then it needs to generate like what drives those mux. Obviously, those are direct inputs. Oh, interesting. Okay. I thought it would generate a mux by basically doing 2-to-1 mux, right? But apparently what it did is... Wait, what did it do? It just implemented an OR in those. But whatever, I mean that works fine. Something I didn't expect, but that's not better or worse. It's just different. Where does that signal come from? Okay, I'm trying to find the out EV way signal. There's a search, I can try that. Out EV. Okay, so there's an out EV way here. How did it generate that? One, two, three, four, five. So I mean the mux logic it generated is a little bit weird. I don't know what exactly it did, but you know what? I have one layer of logic. Here I have 1, 2, 3, 4. I mean, yeah, I had 4 layers of logic, and it generated logic with 6 layers. It generated something that looks like what I expect, which is basically a 4-to-1 mux and then some control logic. I'm not 100% sure of the control logic it generated because it has those inputs driven, but that really doesn't change anything for me, so I'm fine with that. So that signal is good. But as you can see, I mean, that basically all this part that contains, you have 36 LUTs here, and you have 1, 2, 3, 4, 5, 6. So you have 42 LUTs just in that part, which means it seems like it implemented the rest of the logic in really not much, which means I made an error or something. So I made an error in my code. There was no way that implements what I want. But at least the eviction logic, it did that pretty well. So let's go back to the code and see where I screwed up. So, what the fuck did I screw up? The tag width is defined as 12 bits. So the match, I'm comparing the in-way tag with the in-address tag. TL. That's just... Huh. I don't see anything wrong with it. You know what, let's just look at how it generates out hit, because to generate out hit, it has to compare all the ways. So we will immediately see if something is wrong. So let's try to find out it. Out it, okay. That's not a great start. Generated from that lot, and that lot invalid and in mode. Okay, so far so good. Somewhat. I mean, already here you can see it's a little weird because, like, it has a lot here that literally has two inputs set to 0. Like, and here it has a lot with only two inputs, so it could have literally merged that with that. Why it didn't, God only knows. So let's see that input. Where does that come from? Okay, let's see that input then. I mean, what? Oh, wait a second. No, that looks correct. I'm just checking if I screwed up the input mapping basically. Because I mean, that's all that's selected here is supposed to be comparing 12 bits. It's supposed to be a 48-bit comparators. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I got like 12, 13 lots. And there's absolutely no way to implement 4 12-bit comparators in 12 lots. Like, that's just not happening. Which means I screwed up somewhere. Question is where? Does anybody see what I screwed up? Okay, let's try reading the yosys output somewhere. Oh wait, there is something like range select out of band for setting line 71. What is WL? So did I screw up my CLOC2 logic here? You know what, I'm just gonna outcode it to 2 because maybe I screwed up something. Nope, that's not it. Really? Yeah, if plenty of range select out of bounds on signal, whatever. 8691. Way match WL to 0. Oh yeah, I'm an idiot. Okay, never mind. Yeah, no, my C-log2 logic is perfectly valid, but here that's not WL is a constant that I use to store the the number, the ID. Do those in-way valid, in-way dirty? Um, oh yeah, yeah, you're right, Mike. Yeah, you're right. Those need to be array as well. So I screwed up at two places. That this needs to be ways -1 and not WL. And these are arrays as well, of course. Like okay. Yeah. Thanks for spotting that. I should have read the chat like a couple of minutes ago. Okay, so let's try to redo the synthesis here. Okay, so that's more like what I expected, which is slightly more lots than what I can do by hand, and a deeper logic level than I can do by hand. Although I must admit, I think when I did the manual lookup, I think for this signal, I didn't match against invalid and in mode. Anyway, let's have a look at the what's generated. Not your. Okay, that's not up to date, is it? Is it? Wait. Okay, so yeah, it was up to date. So in that corner, we still see our mux, which hasn't really changed or whatever. So it's still all the eviction logic hasn't really changed, which makes sense because the mistakes were not in that part. But here at least we can see that it generated the age. And we can clearly see 1, 2, 3, 4, 5 layers of logic, and we only have 5 layers of logic for this signal, and this signal. Which really isn't too bad. Like if I look at most of the other, those signals generated in 4 layers of logic, and nothing else is deeper in the graph. So really, it's actually did pretty good. No, it's not. I mean, some of the things look like what we designed on paper, some other not so much. You know, okay, that's a bit weird. Why do outway HWE? Okay, let me actually read the usage log again because there might still be something else wrong. Nothing wrong. I'm just looking for messages like that says, you know, stripped, removed, that kind of thing, out of range. I can actually put really good out of. There is no range or out of range or anything like that, which means it's actually pretty good. Oh wow, okay. So yeah, that looks pretty good. And like really deciphering the logic. Some of it, it's somewhat easy to see what it does because it's really what you expect. Like you have a 24-to-1 mux, so sorry, 4-to-1 mux for 12 bits, and so you clearly see the 36 bits here. The control logic is slightly different from what you would expect, but really not that much. It really just pushed some of the control signal in the earlier LUTs, um, which is fine. Um, it might have taken a couple of more LUTs than what you would have done manually, but that doesn't matter too much. These are the various age updates, and yeah, honestly, those are slightly harder to figure out what the fuck it did. I can't really see it right now, but the out hit and the out miss. So it takes the invalid and the in mode, yeah, that makes sense, and it takes this, which is uh honestly, like why is that one named H flat? Like this one is hit way okay. That those three I could understand. Like it's the independent three way. Why this one is named out way H flat? I have no clue. Um, but you can see it takes four signals and merge them, and where do these come from? Uh, they come from here and they merge. So that's an input directly. So that's the valid signal, basically, and then it merged three path, which is in way mem. Where is the in address? In address tag, okay. I'm just trying to navigate and trying to understand exactly what it did. It's not entirely clear at the moment, to be honest. You know what? I'm just gonna comment out everything except out hit. Because I want to see exactly how it did the comparison, the comparison, and this is gonna help me see that. So I did that in 44 LUTs. So just generating out hits, and we would have done it in 36 LUTs. So let's see exactly. Okay, so that's a little more visual of what's happening just to generate that, right? Um, and to generate that signal, it took him 1, 2, 3, 4, 5 signals. So you can clearly see the graph is separated into two parts, right? You have this, and you have this, and they have the same. They have the same structure. So yeah, basically the logic optimization kind of moved things around. Um, like instead of having so if we look at what we kind of came up with, we have like a very hierarchical structure, which is very uh, way by way and regular. If you look at what it actually implemented, it's a little more chaotic because some of the comparison go upper in the tree and stuff like that, which is probably why it results in slightly longer combinatorial path basically, um, and also more LUTs because 44 versus 36, so it's like 8 more LUTs, um, which it might not seem like a big deal, but if you have 10% more LUT usage, on a 5,000 LC FPGA, that's 500 LCs potentially that you're wasting in inefficiencies. 500 LC, that's like the size of the USB core, right? So, okay. Well, I think I'm gonna end here. I will probably write like an optimized version of this. And compare the two. Basically, I'm just gonna rewrite the comparative part. So all of that. Damn it! What did I do? All of that logic I will just say the same, but the way to generate way match would I'll try to instantiate LUT4s myself to generate the comparator exactly the way I want and see what the resulting logic is and what it looks like. If it's any better, if it's worth it or not. Like honestly, given the result at the moment, 104 total LUTs, I would probably go with it, as is, and only go back to it if I have a critical path or if I find that the total number of LUT for the cache is higher than I'd like or something like that. So I would probably leave it alone. But I'm kind of curious because I mean, I was expecting something, in the range from 40, you said 43 plus 45, so like 90 LUTs, and we're at 104, which means we're really not that far off. We have one more layer of logic than I would like, but looking at it, it's really only on 3 signals. Lots of the mux and stuff like that are shorter than that, so I don't think one more logic signal would really justify the effort, because if you have 5 logic layers on every signal you generate, it's going to be annoying. But here we generate most of them in 4 layers. We only have 3 in 5 logic layers, which means that those particular signals will be able to be placed very close to where they're needed, and so because placing one lot is easier than placing 30 lots close to where they're needed. So yeah, I think I'll just conclude here, and I'll write the optimized version kind of offline, because I'm just gonna do that now, but I need to eat first, and possibly just show off the result in the next stream, and then we'll just actually write stuff. I'll probably write some of the Verilog off stream. Things like the SPRAM memory array is really just instantiating the SPRAM and making it somewhat flexible and stuff like that. It's just really boring. But so yeah, in the next stream I'll probably just design, because so far we mostly talked about the bus mode, which is bus access to the cache while it's a cache hit. We haven't talked more about what's gonna happen when it's a cache miss and the actual memory interface and how I'm gonna connect it. I mean, on this stream I looked at what muxes I needed, but we might look at how it's gonna work in more details. I think that's it. So if there are no questions or anything, you can post them in the chat, and if not, thank you for joining the stream. Thank you for watching offline, because I know it wasn't a perfect time for a lot of folks. Yeah, Piotr. But yeah, I know it was like pretty early for you, but I wanted to work on it, and figured people can just watch the stream, or just listen to it and just watch in the background and stuff like that, or as somebody mentioned in ISE, like watch at 2 times the speed, because since I'm designing at the same times, there are sometimes blanks and stuff like that, because I actually need to think. I don't have like the solution written or anything like that. And also, to be honest, I was kind of hoping that tonight you would stream the Rust embedded stuff. So I didn't want to. I wanted to stay to leave the time slot free. And yeah, so if you have any question about what I'm working on, or want to talk to me or anything like that, I would suggest you can either find me on RC in the Ash Open FPGA channel on Freenode as TNT, or actually find me on the 1-bit squared Discord chat. I don't. Yeah, I'm not logged in on this machine, so I can't. I'm not even sure if I can find. Can I find it? Like if you Google for 1-bit square, can you actually find it? Yeah, you can actually find it. I mean, you need to log in and stuff like that, but yeah, you can find me on the 1-bit square chat. Yeah, there you go. He posted Esden posted the link in the chat. So it's 1bitsquare.com/pages/chat, which is, yeah, that's where I was. Okay, so and I'm there as a TNT as well, and there's a FPGA like topic. So there you go. I think that's about what I wanted to say. So thanks for tuning in, and see you next time.